graphs of logarithmic functions. The first example will give you the graphs of 4 logarithmic functions, and we want to find the function form for each graph. If you look at these graphs, the one that is 3 from the left goes through the point 3, 1. This is the basic logarithm graph. So this one is y equals log base 3 of x. Now the graph just one to the right of this goes through the point 3, 0. Therefore, we can safely assume that it's just the main function shifted 1 down. How we show that symbolically is we put minus 1 at the end. So y equals log base 3 of x minus 1. Now let's look at the very first graph that's on the left. This one is the reflection across the y-axis of y equals log base 3 of x. How we show that symbolically is we write negative x in place of x. The graph that remains happens to be the reflection across the x-axis of the first function. So we denote that symbolically with a minus sign in front of the logarithm. Now let's switch gears and think about domains. Notice that for log of x, whatever base 3 in this case, but whatever base, the domain, the allowable x values will be x is greater than 0. So keep that in mind for this next problem. Find the domain of the function f of x equals natural log of x minus 3. Remembering the domain of log functions in the form y equals log base b of x is always x is greater than 0. So therefore, the domain of this function we can find by setting x minus 3 is greater than 0. Therefore, x has to be greater than 3. That's our domain. Right, now that we're talking about domain, let's bring range into it, and let's actually graph a logarithmic function along with its inverse. The function is given as f of x equals natural log of x plus 2. And we have a whole bunch of things that we have to determine about this. But before we do all that, let's start with a simple table of values. And my x values will go from -4 to 4. I'll use a calculator, and I'll find my corresponding y values. Then I'll plot these points. And then I'll connect them with a smooth curve. And this makes sense because it looks like I've shifted the natural log function 4 to the left. That's what the x plus 4 in the parentheses indicates. So I have confidence that this graph is accurate. Now what we want to do is graph the inverse of f. So remember, graphically, well, we could do this one of two ways. We could just switch the x's and the y's in the table, right? And then plot those points and connect those. Another way to do it graphically is to graph the line y equals x and then graph the reflection across this line. So this green function represents the inverse function of natural log of x plus 4. So now let's answer some of these questions. The domain of the original function f, the red function, is x is greater than -4. So we basically want positive values when we're taking the log of anything. Now the range of this function is all real numbers. That's the red function. It will go from -infinity in the y all the way to positive infinity, eventually. The asymptotes. There is one vertical asymptote at x equals -4. That red function will approach x equals -4 but never reach it. How about the domain of the inverse function, the green function? Well, the domain of that is going to be the reverse of x is greater than -4. We're going to want x is less than 4. The range will be all real numbers.